In this video, we're going to do trigonometric integrations. That includes sine and cosine to powers, tangent and secant to powers, and we're going to introduce the power reduction formulas. And these are going to be very powerful tools, the power reduction formulas. We're going to start out with some nice u sub. So if you have a cosine or a sine raised to a power and the other is a singular power, it's just a simple matter of doing a u sub. Of course, u would be the one in which it has the power. So we're going to say let u equal the sine of x, and du is equal to the cosine of x dx. So this cosine and this dx gets replaced with du, and this gets replaced with u squared. So this integration becomes integration of u squared du, which is a nice 1 over 3 u to the third plus c. Don't forget to back substitute, so 1/3 the sine cubed of x plus c. Easy peasy lemon squeezy. Now with b, same kind of thing. We're going to let u equal the cosine of x, and du is equal to negative sine of x dx, and you can see there's not a negative, so it's a negative du is the replacement for the sine of x dx. So this sine x dx gets replaced with a negative du. This cosine squared gets replaced with u squared. This becomes the integration of negative u squared du, and I'll let you finish that one off. C is similar, of course. It has a power of 1/2, so we're going to let u equal the cosine because it has the power other than 1. And du is equal to a negative sine x dx. And of course, this becomes a negative du is equal to the sine of x dx. So the sine x dx gets replaced with a negative du. This gets replaced with u raised to the 1/2. And so this integration is the integration of negative u raised to the 1/2 du. And again, I'll let you go ahead and finish that one off. Don't forget to back substitute. Now, what happens if you now have powers on cosine and sine in which both of them are powers other than 1? Well, if it's odd, I can write the sine, say sine to the third power of x is sine squared multiplied by the sine, which I can then use this identity, the Pythagorean identity, solving for sine squared. Then, similarly, if cosine is odd, I can use this. If they're both even, so one's odd, one's even, you would use 1 and 2. If they're both even, then I can use this power reduction formula. It's on your trig formula sheet. You might see it on the trig formula sheet as 1/2 and then 1 minus the cosine of 2x. This just has been multiplied out. Or, of course, you can do the power reduction for cosine squared. We also have the sum to product, product to sum. So here's a product. It goes to the sum. It's actually a difference, but that's what it is. Again, these are in your trig formula sheets. And this allows us to do some really nice substitutions and fairly straightforward. So on A here, what I'm going to do is I'm going to rewrite this as the integration of the sine squared of x multiplied by the sine of x. Now, I want to keep my angles the same, so I'm not going to use the power reduction. So that's one of the things you want to think about is you want to have the angles match. I could absolutely use the power reduction here, but then I would get the cosine of 2x instead of just x. So instead, don't forget the dx. So instead of a power reduction, I'm going to use the Pythagorean identity. We know that the sine squared of x is equal to 1 minus the cosine squared of x. So then if I do that replacement, this integration becomes 1 minus the cosine squared of x multiplied by the sine x dx. And here I can say, ooh, if we let u equal the cosine of x, and du is equal to the sine x dx. Don't forget that negative sine x dx. So this is negative du is equal to the sine x dx. So here is negative du. This is u squared. So my integration becomes the integration of 1 minus u squared multiplied by the negative du. which then is just going to be equal to the integration of u squared minus 1, multiplying the negative 1 through the first factor, which is the 1 minus u squared, du. Nice, easy integration, and don't forget to back sub. Similarly, I'm going to do the same thing with this cosine shenanigation stuff here. So I'm going to rewrite this as the integration of the cosine squared x multiplied by the cosine of x dx, where we know that the cosine squared of x is equal to 1 minus the sine squared of x. So this integration becomes integration of 1 minus the sine squared of x multiplied by the cosine of x dx. Again, nice, let u equal the sine of x du, a bunch of u's, du is equal to the cosine of x dx. So we know this is a nice u, this is the du, this is u squared. So this becomes the integration of 1 minus u squared du. Nice, easy integration with a back sub. Don't forget to back sub. Let's take a look at C. Now with C, I've got sine to the fifth and cosine squared x dx. So I'm going to take this sine to the fifth and I'm going to write this as the integration of the sine to the fourth of x multiplied by the sine of x multiplied by the cosine squared of x dx. And then I'm going to say, well, just like before, I have the sine squared of x is equal to 1 minus the cosine squared of x. If I raise this to a squared, then I would have sine to the fourth of x is equal to 1 minus the cosine squared of x, the quantity squared. So then this is going to be equal to the integration of 1 minus the cosine squared of x, the quantity squared, multiplied by the cosine squared of x multiplied by the sine of x dx. All I did was rearrange it. And once again, I'm going to say let u equal the cosine of x. Du is going to equal to the negative sine of x dx. Negative du is equal to the sine of x dx. So this is a negative du. This becomes u squared. This becomes 1 minus u squared, the quantity squared. So my integration is, I'm going to pull the negative out front this time. I have u squared multiplied by 1 minus u squared du. And I can do a v substitution here, or, oh, don't forget to square that, 1 minus u squared squared. I can either do a v substitution, so I could say, hey, let v equal 1 minus u squared. I can totally do that. That will make it a little bit easier. Or I can just multiply out u squared. This becomes 1 minus 2u squared plus u to the fourth, and then distribute and just do an integration. Either one. Again, don't forget to back sub. On D, we're going to do something similar. We're going to rewrite this as the integration of the square root of the sine of x. And then this is going to be multiplied by the cosine squared of x dx. Again, I'm going to replace cosine squared with a 1 minus sine. So I have the square root of the sine of x, 1 minus the sine squared of x, cosine of x dx. Once again, we're going to let u equal the thing that has the powers, which is the sine of x. Du is equal to the cosine of x dx. This gets replaced with du. This gets replaced with 1 minus u squared. This gets replaced with u raised to the 1/2. So we took something that was potentially very, very ugly and rewrite this as u raised to the 1/2, 1 minus u squared du. If you distribute that u raised to the 1/2 through, you're going to get u raised to the 1/2, and then minus, I have 1/2 plus 2, which is 3.5. In other words, u raised to the 7/2, or 2.5, excuse me, 2.5, which is 5/2. U raised to the 5/2 du. Don't forget to do your reverse power rule and back substitute. Now, Number E and F. What I'm going to do is I'm going to do the power reduction formula because these are both even. Unlike my previous examples, I had my powers were odd. So I did the separating it as the sine squared times sine or sine to the fourth times sine. Either way, nice replacements using the trig, Pythagorean theorem. This one I'm going to use the power reduction formula. So I'm going to get out my trig formula sheet, and it says that if I take sine squared, the sine squared of x is the same thing as 1/2, and it is 1. Now you can distribute the 1/2 through. I usually don't until the end, minus the cosine of twice your angle. Okay, so then this then just becomes the integration of from 0 to pi of 1/2, 1 minus the cosine of 2x dx, which is equal to 1/2, I'm going to pull the 1/2 out, from 0 to pi of 1 minus the cosine of 2x dx. Now I don't have to do any u sub here, by the way. I can just integrate. So I integrate 1, and that's just going to give me, so I have 1/2. When I integrate 1, that's just going to be x. When I integrate the negative cosine, that is 1/2 the sine of 2x. And then I'm just going to evaluate this from 0 to pi. And I didn't have to do any u sub on that one. Similarly with f, I'm going to go ahead and do the power reduction again, because we know that the cosine squared of 3x is going to be 1/2, 1 plus the cosine of twice that angle, so that becomes 6x. So then this just becomes, I'm going to bring that 1/2 out this time, 1 plus the cosine of 6x dx. And I can just do an integration here. This is going to be 1/2. The integration of 1 is x, plus, and the only way I got cosine of 6x is if I would have had 1/6 out front, the sine of 6x, plus c, and that is my final answer. Now, if we take a look at G, the problem with G is my angles don't match. I have the sine of x multiplied by the sine of 2x multiplied by the sine of 3x. My angles don't match. So I can do this one of two ways. I have the sine of 2x and the sine of 3x. I actually have a product to sum formula. I can use the product to sum formula on my trig formula sheet. This becomes 1/2. And then inside I'm going to have the cosine of the two angles. So I have angle 1 minus angle 2, which gives me 2x minus 3x. And then minus the cosine of adding those angles, which is 5x. So you can see this won't be too bad, at least part of it. And I say at least part of it is because what I'm going to have here is I'm going to have 1/2 the cosine. This is going to be negative x, but cosine is an even function. So cosine is even. Cosine is even, which means the cosine of negative x is just the cosine of x. So I end up with 1/2 the cosine of x minus the cosine of 5x. Now, the problem here is the fact that this is an x, so that's an x, so that's cool. But this is a 5x, but this is an x, that's not so cool. So that may not be my best choice. Let me see, what else can I do? Well, we know that the sine of 2x is equal to the sine of x multiplied by the cosine of x multiplied by 2. That's the double angle. I could use the fact that the sine of 3x can be wrote as the sine of 2x plus x, which then, using the sum and difference, this becomes the sine of 2x multiplied by the cosine of x plus the sine of x multiplied by the cosine of 2x. So then if I have the sine of 2x multiplied by the sine of 3x. This would be the sine to the sine x cosine of x multiplied by the sine of 2x cosine x plus the sine of x cosine 2x. Whew. Okay. Now, this then becomes, remember, this can be wrote as 2 the sine x cosine of x multiplied by this cosine x, so it'd be multiplied by a cosine x. So 2 the sine x cosine squared of x. So this is 2 the sine of x cosine of x. So this first one becomes 4. It should be cosine squared. 4 multiplied by the sine squared of x cosine cubed of x plus 2 the sine squared of x, the cosine of x multiplied by the cosine of 2x. Holy smokes. Okay, now that's just the replacement for the sine 2x, the sine of 3x. So we still need to multiply this thing by the sine of x, because remember, we still have this term of the sine of x out front. So when I multiply this by the sine of x, I'm going to get 4 the sine cubed, the cosine cubed of x, plus 2 the sine cubed of x, the cosine of x, the cosine of 2x. Now the first part here, I can do it by integration, right? I can integrate this by using a replacement for the sine squared multiplied by the sine of x is equal to the sine cubed of x. I could do it that way, and then doing the Pythagorean replacement. Or I can do the cosine squared times the cosine of x, don't drop your angle, is equal to the cosine cubed of x, and then I can use Pythagorean identity to replace those. So that's not a problem. That's easy peasy lemon squeezy, not anything really exciting on that part. Now the second part here, this is the problem child because I have the angles don't match. But with cosine, by the way, I can replace cosine 2x as multiple choices. But if I use 1 minus 2 the sine squared of x, then 2 the sine cubed of x multiplied by the cosine of x multiplied by 1 minus 2 the sine squared of x then gives me 2 the sine cubed of x, 1 minus 2 the sine squared of x, and then the cosine of x. And then when I do this integration, obviously this part, this term of the integration would be u is equal to the sine of x. That way you can get the du is equal to the cosine of x dx. So even though this was, holy smokes, this gets really large, all of this can be brought down to nice u sub at some point using your trig identities. All right, now what happens when we have tangent and secant? Well, we know secant squared is the derivative of tangent. We know secant tangent is the derivative of secant. Tangent, if you remember, can be wrote as sine over cosine. So that becomes, we have the natural log of secant x is the integration absolute value of the tangent. And then the secant can be wrote as 1 over cosine. And then this is why this works out. Let me talk about why this one works out. This one was like, what? First time I seen it, I was like, what? So let's look at this. The secant of x, secant of x, if I multiply it by the secant of x multiply plus the tangent of x, this is where this one comes from, over the secant of x plus the tangent of x. So in other words, I'm taking the secant of x and I'm multiplying it by 1. This becomes the secant squared of x plus the tangent of x, the secant of x, over the secant of x plus the tangent of x. Now, if you notice that this numerator, if I rearrange it, is the derivative of the denominator, that's why this one ends up working out as the secant, the integration of the secant of x dx is equal to the natural log, is because what you do is you multiply the numerator and denominator by the secant of x plus the tangent of x. The numerator then becomes the derivative of the denominator, so that means it must be a natural log. So that I just wanted to share that with you. For this first one, it's a nice, easy u sub. We're going to say let u equal to the tangent of 2x, and du is going to equal to the secant squared of 2x dx. So this gets replaced with 1/2 du, because remember I don't see the 2 there, so I have to make that adjustment. This is just u to the 5th, and so I'm really integrating 1/2 u to the 5th du. And nice, easy integration. Don't forget to back sub. Similarly, take a look at this, man. This is another one. Notice that the derivative of tangent is secant squared, so we're going to let u equal the tangent of x over 2. Du is going to equal to 1/2 the secant squared of x over 2 dx. That means this gets replaced with 2 du. This integration becomes u multiplied by 2 du, and nice, easy back substitution. And in fact, C is similar, right? C is like, whew, we like C. C is let u equal, again, the tangent of x, and nice, easy substitution. So really what I want to do is I want to focus on these. What happens? What happens when I have one of my secants or tangents don't have just one as an exponent? They both have exponents other than 1. Well, if the exponent on the secant is even and bigger than 2, then I can write the secant to like the 4th power is equal to the secant squared times the secant squared. And then I can use the Pythagorean identity. Now this Pythagorean identity is one of the ones that you'll see on your trig formula sheet that I give you for every test. So nice, like trig replacement here. If k, which is the exponent on the tangent, is odd, then I can write that as the tangent raised to 1 power less of x, the secant 1 power less of x, and then my u would probably be the secant. And don't forget to do the Pythagorean identity for the tangent squared. If k is odd, larger than 3, and j is equal to 0, then I can write k to the 5th power, say, as tangent to the 5th power of x is the tangent to the 3rd power of x times the tangent squared of x, replacing the tangent squared with secant squared minus 1, the Pythagorean identity, and then we have a nice u sub. If k is even and j is odd, then we're going to just go ahead and write tangent squared is equal to secant squared minus 1, Pythagorean identity, and express tangent of k in terms of secant and use integration by parts to integrate all the odd powers of secant. So let's go through some examples. I'm not going to do them entirety, but I am going to get them set up for you. Now the first one is straightforward. There's actually no work. The derivative of secant is secant tangent. So the first one, no work. This is just going to be the secant of x plus c. That's really nice. The secant of x is the derivative of secant tangent. We have the tangent of 5x. Well, I can write the tangent of 5x as the sine of 5x over the cosine of 5x dx. And you can see that if we were to let u equal the cosine of 5x, and du is just going to be negative the sine of 5x and dx. So this then becomes the negative integration of 1 over u du. Don't forget the 5. This should be negative 5. So this needs to be negative 1/5 out front. So then this just becomes the negative 1/5, the natural log of the absolute value of the cosine of 5x plus c. And you're like, but don't we have a formula for this? Wasn't this like when I did the integration of the tangent of x dx, wasn't that the natural log of the secant of x? And the answer is yeah, because, now this is why. We have the natural log of x raised to the r. We can bring that r exponent out front. This is the natural log of x. So this negative can come in to the absolute value as an exponent. So then this is equal to 1/5, the natural log of the absolute value of the cosine of 5x raised to the negative 1 plus c. So this becomes 1 over the cosine of 5x, which is the same thing as the secant. So 1/5, the natural log of the absolute value of the secant of 5x plus c. And that's the formula. Now, I want to be clear that I am totally fine if you use this or if you give this answer. Either one I am actually totally fine with because they are equivalent, just so you know. Let's go back and look at our next example here, which is the tangent squared, x secant x. What we're going to do is we're going to rewrite this as the tangent squared of x is equal to the secant squared of x minus 1. So this is integration of the secant squared of x minus 1 multiplied by the secant of x dx. And you're thinking, how did that help me? Well, just wait. I'm going to go ahead and distribute through, and so we get the secant cubed of x minus the secant of x dx, which is the integration of the secant cubed of x dx minus integration of the secant of x dx. Now, we can now treat each one of these individually. So, let's start with the secant cubed of x. Now, the secant cubed of x can be rewrote as the secant squared of x multiplied by the secant of x dx. We still have the minus the integration of the secant of x dx. So we'll just leave that alone for a minute. Now let's consider doing this first integration by parts. So we're going to do integration by parts. We're going to let u equal the secant of x, and then du would equal to the secant of x, the tangent of x dx. That means dv would equal to the secant squared of x dx. That means v would equal to the tangent of x. So just focusing on this first integration part, I'm just going to focus on this part. This is going to be the integration of the secant squared of x multiplied by the secant of x dx is going to be equal to, by parts, we're going to have the secant of x, the tangent of x minus. We're going to have the integration of the tangent of x multiplied by the secant of x multiplied by the tangent of x dx. So we know that this piece then becomes the integration of the tangent squared of x multiplied by the secant of x dx. And this is where we kind of started. So let's go back and revisit where we are. So this integration of the secant squared of x multiplied by the secant of x dx minus integration of the secant of x dx, which started out as, so let me start it what I started out with, which started out as the integration of the tangent squared of x, the secant of x dx, is equal to this. But we know then that the tangent, the integration of the tangent squared of x, the secant of x dx, is equal to, now the stuff in blue, which was the secant of x, the tangent of x, minus the integration of the tangent squared of x, the secant of x dx. That's all of this piece. Plus I still had this minus the integral of the secant of x dx. So Notice how this and this match, so I'm going to bring this to this side. So I'm going to have 2 of those. So I'm going to have 2 the integration of the tangent of x, tangent squared of x, the secant of x dx. Now we've seen this with integration by parts, so this stuff keeps repeating, is equal to the secant of x, the tangent of x, minus integral of the secant of x dx. So then I just divide everything by 2, and so I get the integration of the tangent squared of x, the secant of x dx, is equal to 1/2 the secant of x, the tangent of x, minus 1/2 the integral of the secant of x dx. And if you remember earlier that the secant of x, when I integrate this, remember I can take the secant of x and multiply the numerator by the secant of x plus the tangent of x, divided by the secant of x plus the tangent of x, which gives us the natural log. So this is going to be equal to 1/2 the secant of x, the tangent of x, plus, minus 1/2 the natural log of the absolute value of the secant of x plus the tangent of x plus c. And that's it. And that's because I had to do integration by parts. And it was that one of those integration by parts that just keeps expanding out. If I stop and realize that when I do the integration by parts, at some point, if this happens, if this and this, I have it on both sides. Remember, I can always bring it to the other side, divide by that coefficient, and solve. That was a lot for that problem. Let's take a look at the next problem. Oh, look, I'm going to have to erase this. So give me just a moment just to do some erasures. Just kind of kick back. That always happens when it doesn't lock with the screen like I want it to. And let's go take a look at the cotangent up here. And the cosecant. Now you're like, wait a minute, we haven't done tangent, or we haven't done secant and cosecant, cosecant and cotangent, and that's true. That is absolutely true. We're going to do similar things with the cosecant when we see cosecant as when we had secant, and we're going to do similar things when we have cotangent as when we had tangent. Now, if you remember what I did when I had just secant, I multiplied the numerator and denominator by secant and tangent. I'm going to do something similar because I know, this is what I know. I know the dx of the cosecant of x is equal to negative cosecant of x, cosecant of x, the cotangent of x. And I also know the derivative of the cotangent of x is equal to the negative cosecant of x, the quantity squared. So I'm just going to move that out of the way. I'm going to multiply this by a negative. I guess it doesn't really matter if I use negative. I'm just going to use a negative cosecant of x and a negative cotangent of x, numerator and denominator. So that what I'm going to, and there's still a dx there. So that when I get done, what I'm going to get is I'm going to get negative cosecant squared of x minus the cosecant of x, the cotangent of x, all over, in this case I'm going to pull out a negative, the cosecant of x plus the cotangent of x dx. And we know then that the denominator, if I take the derivative of the denominator, I'm going to get the numerator, so that means it must be the natural log. So this is equal to the negative natural log of the denominator, which is the cosecant of x, plus the cotangent of x plus c. So just like we did when we had secant, except for we just have to deal with the negative parts. Cotangent, of course, we can rewrite easy peasy lemon squeezy as the cosine of x over the sine of x dx. Nice replacement there. We let u equal sine, and so we're going to get the natural log of the absolute value of the sine of x plus c. Nice easy peasy lemon squeezy. For my next example here, problem I have is I have the square root of the secant. Well, actually, that's not really the problem. I can rewrite the tangent cubed as the tangent squared multiplied by the tangent, and I have a replacement. So this is what I could do. I have the tangent squared x multiplied by the tangent of x, which is tangent cubed, which then gives me 1 minus the secant squared of x. So secant squared of x minus 1 times the tangent of x. And the problem is that I can't let u equal tangent. If I let u equal tangent, then du would equal the secant squared, but that isn't going to get me what I need. And I can't let u equal the secant because I need secant tangent as its derivative. So what I'm going to do is I'm going to say, well, wait a minute. Let's go ahead and multiply the numerator by secant and the denominator by secant. Don't forget you still have the dx there. Because I can multiply the numerator and denominator by the same thing. And so then I'm going to have the integration of, I'm going to have the secant squared of x minus 1 multiplied by the tangent of x, the secant of x, over the secant of x multiplied by the square root of the secant of x dx. Now you're thinking, why did I do that? Well, because if I let u equal the secant of x, du needed to have a secant of x and a tangent of x dx. Now I can say this gets replaced with du, and everywhere I see secant, I get replaced with u. So this becomes u squared, this becomes u raised to the 1/2. So what I really have is the integration of u squared minus 1 over u multiplied by u raised to the 1/2 du, which now is not that bad of an integration if, let's just do this. Let's rewrite this as u squared minus 1 over u raised to the 3/2 du. Let's go ahead and distribute the u raised to the 3/2 underneath each one of those two terms in the numerator. And so I have u over 2, or u squared over u raised to the 3/2 minus u raised to the negative 3/2 because it's 1 over, and then du. Now I end up with the integration of u raised to the 1/2 because I have 2 minus 1/2, which is 1/2, minus u raised to the negative 3u du, and then of course, nice easy peasy, reverse power rule, and then don't forget to back sub. So not too bad. Here is my last one. I have the secant squared of x minus 1. Well, the secant squared of x minus 1 is equal to the tangent squared of x. So then the square root of this is just the square root of this. So this really is from negative pi thirds to pi thirds of the tangent of x dx. Now, tangent is odd. So if you were to graph the tangent, right, this is the graph of the tangent. So if you go from negative pi thirds to pi thirds, this area and this area are equal. One's positive, one's negative, so the answer is 0. And that's it for this video.